Hello, good morning, one and all. I welcome you again on the third day of session 3 of the FDP. Today's discussion topic is state variable system modeling, as you find on the screen. Today's session will be mainly done by chalk and board, so there is no PPT as such made for topics today. Reason being, state variable system modeling requires some hand calculation to be done. And if you really want to get the feeling of the whole course, whatever is being done today, some scribbling is required from your end. So please, if you don't have a pen and paper, please arrange for pen and paper and start solve some numericals. When some proofs are being done, please get some pen and paper and start scribbling with me. I'll first show the topics for today that will be covered. State variable will be built from the very scratch. First, I'll tell you what is meant by state variables, a basic explanation of that, what are the different matrices that is used in the state variable. We have already seen yesterday what is transfer function based approach of system modeling. So what is the difference between transfer function based modeling and state variable modeling? That will be seen today. What are the advantages of state variable model over other, that also will be explained. Then we will see a system equation, LT, CT, LTI system, and how this CT, LTI system can be modeled by ODE. Already we have seen that yesterday. How the same system can be modeled by using state variable, that we will see today. Switch from ODE to state variable. How can we switch from state variable to ODE? How can we get the system schematic? How can we get the system transfer function? We will see today. Then comes the very important thing, calculation of state transition matrix e raised to capital AT. T is nothing but the exponential of e raised to AT. So capital A is nothing but the state matrix. We will see that how to calculate e raised to AT. And then we have seen the solution of ODE. Today we will see solution of state variable system for homogeneous system and non-homogeneous system. If time permits, we will see what is observability, which is also called as Kalman observability, and same thing, interrelationship between system parameters. Whatever we have seen yesterday, it goes in the same line. Finally, state variable model development from engineering field. So model development, we are having our 5th day. On that day also it can be done, but at least I would like to take you to the field of controllability and kernel observability. So this is today's target. So this much PPT explanation was there. Now we'll go live and through camera. Please follow what is being shown on the board. Good morning once again. To see the basics of state variable, what is meant by state space analysis, what is state variable system model, and first in that I would like to tell you what is the difference between transfer function and state variable model. Why state variable, why state space is required. Yesterday we have seen transfer function based model. One very important thing I did not show you, that is, if we are thinking that T is the system input, HT is the system, HT is the system function, then we have seen on the first day, that is YT is equal to XT convolution HT. So this is how the system output is calculated. But in this case, I am showing only one system. If I extend this block diagram like H1T, and there is another block diagram like H and H3T and so on, then I am finding YT. Calculation is easy. That will be XT convolution H1T convolution H2, and we will go directly find the YT output. Problem with transfer function based modeling is, if I want to get for any single system, if I want to check what is the dynamics of this system, how this system is affecting the output yt. That cannot be found out by transfer function based system. This system only gives us overall system dynamics. Transfer function based system modeling gives us overall system transfer function. But separately, if we want to get any intermediate system dynamics that cannot be found out by transfer function based system modeling. And this is a very big drawback of transfer function based system modeling. We can get intermediate system dynamics, we can get overall system dynamics, and if it's a system based, if a system is comprising 10 variables, we can get dynamics of all 10 variables, we can get equation of all 10 variables by using state variable system. So this is why mainly state variable system analysis is preferred over transfer function based system. So that is the first point, that is internal system dynamics. Second point, transfer function based system modeling. Generally we are trying to model LTI city system. So if the system is linear, if the system is time invariant, then only we can use transfer function based system modeling and get the transfer function. What about nonlinear system? What about time invariant system? Can we model nonlinear time invariant system by using transfer function based modeling? Answer is directly no. So if the system is nonlinear, we cannot use transfer function based system modeling for accurate modeling of the system. So second point is very, if the system is nonlinear, if the system is time variant, then the transfer function based system modeling cannot be used. In this case, only system modeling, or we will call it as SVM. In that case, only state variable system modeling can be used. So with these two acts, we will go forward for the definition of state. In state variable system modeling or SVM, what exactly is meant by state? Let me give circuit and let me give you the same equation what we have seen in last two days. Take a LCR circuit. So this is some circuit with input as Vt. This is resistance, inductance and capacitance. Easiest circuit we have seen the modeling many times. What we find is generally output equation IT. Input given is Vt. This can be sinusoidal, this can be unit step, some supply we are giving to the system. This is resistance R, this is L and this is C. What we do is we can write down the equation in Laplace domain. Before taking it into the Laplace domain, let us find out what is meant by state. In the domain, what we have found out is it was IS or output by input, or there was the transfer function. This was something like denominator was an equation of a square plus r by a. Order is 2, as LCR system is having order of 2. In that case, there will be 2 state variables required to actually explain the system dynamics. Okay. If it's a third order system, we have to define 3 state variables. As this is a second order system, we want to define all the system variables. We want to capture the whole system dynamics. At that time, 2 state variables are enough because there are 2 energy storing elements. And one more thing, that state variable system analysis, the output of that is same for everybody. Everybody might model the system in a different way. Okay. So the way we are defining the variable, that way we are going to get the system model. In this case, somebody can take 2 variables and the whole system dynamics can be explained by means of those 2 variables. Which are the variables we can take? For my ease, what I mean is 2 system variables, they have to be time dependent. One have to be VCT. So this is one variable which I am defining, that is capacitive is one state of the system. What is the another state? Another state can be IT. This being a series circuit, inductor, resistor, capacitor components are
carrying same amount of current.
So all the components are carrying same current, which is IT. So in this case, 2 states are IT and VCT. What is the definition of state? Definition of state is
First thing is the count of state is equal to of energy storing element in the system. And second thing, what is meant by state? State are the variables which together will define the whole system dynamic should be missing. So this is the definition of state. If you want the exact definition as found in the book, they say that the state is a minimal information that is sufficient to determine the output of the system for all time. For all time means time starts from t is equal to 0 and time goes up to t is equal to infinity. Doing a causal state variable analysis, that's why time starting from 0 and up to t is equal to infinity. So it is the minimal information. So minimal information captured by IT and VCT. So together they are capturing the minimal information, and that information is captured from t is equal to 0 up to t is equal to infinity. So what is meant by state variables? The definition is variables that contain this information are called as state variable. Again I am cautioning you that state variable is not unique. In this case, somebody will say, yes, IT, I will take, instead of VCT, I will take VLT as another state variable. Am I right? Answer is yes. So VLT and IT can be taken as a set of variables. So instead of one, you are taking two variables. This is one set. This can be another set. Somebody will say, I will take VRT and VLT as a state variable. Is the designing right? Answer is again yes. Okay. So state variable depends on what actually we want from the circuit. So there is not a single way of defining the system. The system can be defined. So this is the simple, very basic of state variable. So first we have to understand that number of energy storing element is equal to. Now what happens if I define three states for this second order system? So I will say that I will take inductive voltage, circuit current, and I will take capacitive voltage. Three variables I will take to define a second order system. Am I right? Answer is, to do a small work, you are putting. So this is a second order circuit, and to define a second order circuit dynamics, you need maximum two variables. Any two variables you can take. In this case, to define a dynamics of a second order system, if you are taking three variables, that means the system is called as overdetermined. That means we are using extra resource to solve a very limited amount of the problem. So we should not define overdetermined system, we should not model overdetermined system. Hence, knowing how many energy storing element in the circuit is very important. Hence, knowing the system order is very important. And after that, we will define what is called as number of state variable for any system. So with this basic understanding, the next topics, that is number of states should be equal to the number of energy storing element within the network. So there is a very basic rule. For continuous time system, they are adder, amplifier. So whenever we are converting state variable analysis into the system schematic, in that case, for CTLTI system, we will show that we are using three basic circuit components or three basic system components. One is an integrator, one is a differentiator, and another is an amplifier. Choice of state variables, this is very important. Choice of state variables for a system is not unique. There can be many state variable matrix representation for a single system depending upon the states or variables defined by the user. So whenever we are setting this kind of question for the exam, we have to remember that every student can have a different kind of choice of system variables, and the answer will be different for all students. It is possible. Hence, we should be knowing the overall system state variable. So more than the answer, the process is very much important. So how are chosen, how state variables are modeled, which system dynamics is captured. So for state variable, one more thing is there. We have to define what is the output quantity. That IT and VCT, they are the state variables which are defined in the system. Somebody might say that yes, I will want that VLT for my system output. Now define what is state variable. Somebody will say that you take this and this as the variables of the state, but take VR, that is voltage, as the system output. So system output is generally given by YT. So this is also another thing we have to define if we want a state variable representation. So these things are very fluid, these things are very much dynamic. How to find the state variable model, we will develop that model. So this was mainly the basic introduction, that why state variable, what is the difference between state variable and transfer function is defined, what is state,
and how to define state variable. And state variable cannot be unique for everybody, it can be different for different kind of. Let us take a very simple modeling, and for the same circuit I will draw it little smaller, and we will develop what is the state variable for RLC. So the same circuit I am drawing. So for my ease I have made some step here. So this is called as VT, this is called as R, this is L, this is C, and this current is I. Okay. Question is, model this system for state variable analysis, or show the SVM, state variable model, for this system. Okay. What I'll do is the same old second order differential equation that I will write for this system. So the equation will be something like this. So VT, whatever voltage you are supplying. Now one thing of caution I would like to tell you, that mechanical people and computer people, you are thinking only I am taking the from the field of electrical or electronics. It is not like that. I'm giving you a dynamics, and after I write the first equation, you no need to remember what's happening in the circuit. So just follow this equation afterward. So just to develop it, and once I draw this equation, forget this part. You can take MBK system as well. Okay, so that is ms square plus bs plus k, that is the mechanical system. It also can be taken here. So don't think it is being skewed towards ENC. It is not like that. From here to here, how I am writing the equation, that much is very much, and afterward we can take it to any domain. So only follow this mathematics. This part is not very important. Okay, so how much is VT? VT is equal to into IT, that is the resistive voltage. We know this, we have studied this thing in 11th and 12th, so this is very simple. And then L dit dt plus 1 by C integration of dt. Okay. Even if you cannot see, you cannot, I don't know whether it's very clearly visible or not, but at least you can write this equation. That is VT is equal to inductive resistive voltage plus capacitive voltage. So VT is equal to RIT plus L dit dt plus 1 by C integration of IT dt. This much is there. What I told you was there are two state variables. One is called as VCT. So VCT is different from VT. VCT is the capacitive voltage, VT is the input. This VT can be sinusoidal, this VT can be step, this VT can be anything. That is not our lookout. How to form the state variable? Now for state variable, the standard system equation is x dot t is equal to axt plus but. Now this is a new set of equation, please write it down, which is called dot t is equal to axt plus but, and yt is equal to cxt plus dut. So this is the modeling circuit and this equations in this model. Okay, what is meant by xt? Xt are called as the state variable. What is called as x dot t? X dot t is the of state variable. So what we are supposed to find out is a ODE kind of a relation. So we are supposed to represent x dot t as axt but. What is ut input? In this case ut is same as vt. So xt is state variable, ut is the input, same x and ut is there in the second equation also. What is yt? Yt is nothing but system output, and we have to define what output we want for this system. So the state variables are not one. For this system, state variables are two. So state variables xt for this system we write in the form of vector. One is it, another is vct. So please keep writing. This is the dimension of xt for this system. So what is this dimension? Dimension is nothing but matrix dimension, 2 row 1 column. So this is the dimension of xt or state variable. So what is xt of this xt? What I will write is, I will write it and vct. What I'll write here, x dot t, x dot as it dot and vct dot. Okay. So again I'll repeat, this system is how, for this system I have defined two state variables. I am defining state variables as current and capacitive voltage. Somebody wants current and inductive voltage, welcome, nothing wrong. Okay, so in this case the state variable xt, because this is the problem formulation or model formulation, in this case is represented by a set of parameter in the vector form. Okay, so this is the vector representation of system parameters or state variable parameters. So this is it and vct. Here I write the same thing but in dot format. So this is I dot t and this is vc dot t. What is ut? Ut in this case will be same as vt. Here also I will change it. So in this case this is vt. xt again I'll change it. So this will be it and this will be vct, like this. So this is kind of a, don't know now. So this yt I am told you what is output. Output also I will keep as vct. It is possible, or output can be same as it, be vlt. Anything we want we can get. So for this case initially what I will say as output parameter is circuit current. So state variable and output can be same. So in this case what I am saying is output is equal to it. This has to be defined by the user. So if you are setting a question paper, I have to define how much is the what is the output variable I want. So in this case I am giving state variable as it, output also as it. Now define what is the state variable model. So what is not known? Not known is A matrix, not known is B matrix, and not known is T matrix. So designing state variable model is nothing but from this set of equations, A matrix, what is B matrix, what is C matrix, and what is D matrix. This is what is meant by state variable modeling. And from where can we get? We can get all this matrix from the set of equations. Now how many state variables are there? In this case there are two variables. As there are two variables, dimension of A matrix will be 2 by 2. So we call that there are two state variables. N is equal to 2 because there are two energy storing elements, because system having second order thing. So as two state variables, as n is equal to 2, as order of the system is equal to 2, this A matrix will be n by n, this 2 by 2. So this kind of understanding is required. If it's a three-dimensional system, then this thing will be 3 by 3. What is B matrix? So this one is number of inputs. This is number of state variable. Cross n A matrix, system matrix, B matrix will be n cross input. So as there are only one input, you can see there in this system only one input. So this dimension 1. What is YT or what is C matrix? C matrix is called as output matrix. Okay, and as there is only one output, okay, for this system, 1 cross 2 or output cross n. So this is n cross number of inputs. This is order cross 1. What is n? N is number of state variable. So this is what you have to remember. And what is number of state variable? That is same as number of energy storing element in the system. So n cross n, 2 cross 2. B matrix will be having dimension of n cross input. So there are two variables, and so this thing will be having 2 cross 1. C matrix will be having dimension output cross n. So output is 1, there is only one output for the system, and there is order of the system. So this will be output cross n, and there is a D matrix. So this will be output cross n, and there is a D matrix which is called as direct transmission matrix. Okay. So this is input. So in this case, as there is only one input and one output, the dimension of the D matrix will be 1 cross 1. So this will be not be in a matrix form, this will just be in a scalar form. So this will be just a figure, that's all. So finding A matrix is the most important thing for any system. Okay, so this is the biggest size of matrix. So A matrix will be n cross n, 2 cross 2. Matrix will be 2 cross 1. C matrix will be 1 cross 2 because only one output and two state variables, and D matrix will be input cross output. There is one input, one output, D matrix will be 1 cross 1. So all this we have to find, and that will be the definition of state variable for this system. One very big advantage of state variable system I did not tell you, That is, state variable can model what is meant by MIMO. It is called multi-input and multi-output. If you remember yesterday what all models we had done, every some output quantity Laplace divided by some input quantity Laplace. We were taking this input quantity Laplace to the right side, and this was transfer function. What is yt by taking inverse Laplace transform? What is the difference between this system and system? Every time in previous 2 days we have found system where only one input was there, only one output was there. So that is the restricted kind of modeling. Function based modeling is giving us output equation only when there is only one input variable, only one output variable. But if the system is like this, multidimensional, or it is also called as robust system. What is meant by robust system or MIMO system? There can be many inputs, there can be many outputs. In that case, how to get the state variable system equations? So in this case, we were getting previous days, we are getting only one output equation, that is yt is equal to something e raised to minus 2t or something. If the system is multidimensional, if the system is having many outputs, if the system is having many state variables, if the system is having 10 inputs, then how to get the overall system model? Transfer function based system modeling cannot help you there. For those kind of modeling, by using computer, we have to study or we have to understand this state variable modeling, or which is also space based modeling. So this is another name, subspace based system modeling, or state variable modeling, or state space based system modeling. So now is why state space? So mainly to know the internal dynamics of the system, that is the first point. And second thing, to model multidimensional system, we have state variable system modeling. See a very simple example, the same example I'll be going through. So I have actually laid the basics. What we are, t is equal to rit and L dit dt and 1 by c it dt. Okay. Second thing, as there are two state variables, I'll write this equal that there are two variables. One is called as it, another is called as vct. So these two equations we should know. How to model vct? Capacitive voltage 1 by c integration of it dt. That's all. Take differentiation in both the circuits. So what I find is vc dot t or d vct dt is equal to it by c. So this equation we have to remember. Okay. So vct, capacitive voltage 1 by c integration of it dt, visible. Okay. So in this case, vc dot t, just take the differentiation in both the sides, that will be equal to 1 by c here. So 1 by c d vct dt, like this, and 1 by c d vct, sorry, this is not it by c. So this v dot c is equal to it divided by c. I think this is correct. Okay. So vc dot d vc dt, and in the right side this thing gets differentiated, so what we get it divided by c. So this equation we have to remember, I'll write it here. So vc dot t is equal to it by c. So one equation is done. We want equation of it dot. So this is another thing we want, because I told you that what is the model of dot t is equal to axt, and I told you that this xt is nothing but it and vc in vector form, like this. So you want a equation of it dot and you want equation of pt dot, like this, axt plus but. We know what is but, and this dimension will be 2 cross 1. Okay. So this matrix we are supposed to find. So vc dot is equal to this one. Let us find out what is, how can we find it dot? The top equation and see if there is anywhere it dot is there. Just take some time and just find out from this equation, which is a very basic system equation, how we can change this equation. So vt will be same, so I am rewriting this equation, vt is equal to vt. Take it outside. Okay, so what are you finding? This r into this plus l. What is this term? This is dit dt. Can I say that this is IT, or I can say that this is I dot T. Can I say that? Okay, I dot T. I dot T is nothing but dit dt plus 1 by C integration of it dt. What is that? This is nothing but VCT. So this line, try to understand this. So first line is VT, input voltage, is equal to resistive voltage, inductive voltage, capacitive voltage. Second line, in T is kept as IT only. This is one state variable. And this dit dt I am representing as I dot T. And this L remains as L. And this is the capacitive voltage. This voltage is nothing but VCT. Rewrite this equation. Take this thing in the left side. So this is L RT is equal to, so VT minus IT. So this thing comes this side minus. So more than signs, this what? R is missing. So where is the R? This is R. So R will come here. R will come here. Okay. So more than science, this state variable system model development is more of an art than science. Okay, and we have to master this art. So there is no standard procedure. We have to just see the overall system equation and we have to keep it so that we can come to the final state. So what I have done is I want I dot T because I want to get this x dot T is equal to AXT. We are trying to find out a system matrix first. Okay, so for that L I dot T I have kept here, and the remaining thing is like this. Finally, I dot T is equal to, take this L below, R by L of IT minus 1 by L of VCT plus 1 by L of VT. So don't confuse between VCT and VT. VCT is voltage and VT is the input supply voltage. So now this is another form. Now this is another form and this is another equation. So I have got, first equation is I dot T is equal to minus R by L IT minus 1 by L VCT plus 1 by L VT. Second equation already it was done, that was VC dot T is equal to IT divided by C. So these two equations. Now if we write these two equations in matrix form, that itself becomes the state variable system model. So these two equations has to be in matrix form, and how to write it? So that is the trick, and only from these two equations we can get what is called a state variable model. So what is the state variable model? This is x dot T is equal plus BUT. So from these two equations we can find out the first equation of state variable. How can you get that? So what is our states? State is nothing but IT and VCT, and left side it is dot, so it will be IT dot and VC dot. Okay, next is equal to VC dot, we will see later on. First let us find out A matrix. And what is XT? XT is IT and VCT. Dots you write here, same variable without dot you write here, plus B matrix. So B matrix I told you it is 2 by 1. Why 2 by 1? Because it is n cross input. Now there are two state variables, that's why this will be n is equal to 2 and there is only one input. So this will be 2 by 2 because this is n cross n, and this will be 2 cross 1, this is n cross of VT. That's all. What is VT? So instead of UT in the standard equation, we are writing VT because our system is having input supply as VT. Now can we write these two equations in? So let us see. I dot T is equal to how much of IT? So I dot T is equal to how much of IT? So in I dot T, how much is the bearing of IT? It is R by L. Okay, so this is the first equation we are writing. In I dot T, how much is the bearing of VCT? It is minus 1 by L. So this is the first equation. So I dot T is equal to T minus 1 by L of VCT. What's remaining? Remaining is this part. This is nothing but input. So this first part will be 1 by L. See, first equation is, okay. So I dot T is equal to minus R by L of IT minus 1 by L of VCT and 1 by L of VT. That means B matrix is having bearing on input. Second equation, V to IT by C. IT by C plus I can write 0 of VCT plus 0 of VT. So these terms were not there. I am just adding it because state variable has to be represented, state variable dot has to be represented in terms of state variable and input. So that's why equation is only this much, IT by C. So how much of VCT is there? Nothing, 0. How much of input is there? Nothing, 0. Now represent this equation in this form. So VC dot T is equal to, what is the P? 1 by C. Okay. How much of VCT? VCT bearing is 0. So this equation is this into this plus this into this plus how much of input? Input quantity is also 0. Done. Okay. So this is the first equation. So first equation is developed from the very loop equation of Vt is equal to RIT and all those things. We have to rearrange the term IT dot, and IT dot has to be represented in terms of other state variables IT, VCT and VT, and write the equations and write in the A matrix. Now A matrix is minus R by L, minus 1 by L, 1 by C and 0. And what is the B matrix now? B matrix is nothing but 1 by L and 0. Okay. So this is what is called as state variable. So minus R by L, minus 1 by L, 1 by C and 0. That's all. There is another set of equation YT, and how to do YT? So this is mainly more difficult thing. What is YT? YT is equal to CXT. What is XT? Is equal to CXT plus DUT. Okay. So YT is equal to, I have defined that YT is equal to IE. This is defined. This is I am defining it. The designer is defining it, that I want output to be the circuit current. Can I write this equation? Can I write this equation this form? YT is equal to CXT plus DUT. So this equation I am writing, and I have to replicate this because this is the given condition. So YT is equal to what is the dimension? Dimension will be output cross N. What is N? N is equal to 2. So I want only one output from the system. So this will be 1 cross 2. And then XT. What is XT? Is nothing but state variable IT and VCT plus D. D is 1 cross 1 because there is only one input, one output, and this of VT. The equation you have to write in this format. This is the equation. So YT is equal to IT plus 0 VCT, I can say. So what will be this thing? This will be 1 and 0. That's all. Okay. So what is YT? YT is equal to 1 of IT. YT is equal to 1 of IT plus 0 of VCT. So this equation is actually pointing towards this. Understandable? Okay. And there is no input quantity in this output equation. It is possible that there is some input present in output also, because there might be a direct transmission. So just after input, in block reduction, take this kind of numerical, that is, you are giving XT and there are intermediate blocks, and this is YT, and there comes a link like this. Okay. So this is the input and there comes a link like this, direct. So part of input, in such cases D matrix will be existing. But if you are finding that this kind of things are not there, there are loops here and there are loops here and all these things, in such cases D matrix. So D matrix, very specific case, this is called as direct transmission matrix. So if input and output directly connected by some path, in that case D matrix will appear. But this system is not like that. This VT is not directly connected to output. The output is nothing but what is output? Output is nothing but IT. So there is no direct connection. That's why in this case will be equal to 0. So D matrix is not present here. So this is the kind of a state variable representation of the system, second order system. So to know it, again I'll just give a small recap. This because there are only two state variables. This will be 2 by 1 because n cross input, only one input to the system. If the system is there, there is another rung here, there is another RLC circuit and there is another input. Okay, so V1T and V2T, in that case we have to take two input conditions, and both this I dot T and VC dot T will be having some two loops. That is more difficult numerical, we might see in it later. Okay. So in this case, as there is only one input, this is cross 1. In this case YT is self-defined. The designer has to define it. I am defining YT as IT. So this is the model where YT is equal to IT. Okay. Like this. That's why I am finding YT is equal to 1, 0. Move it. This is not required. So this is called C matrix. So if you want to say what is A matrix is minus R by L minus 1 by L 1 by C, and matrix B matrix is 1 by L and 0. What is C matrix? C matrix is 1 and 0. So this is what is called as state variable representation for the given system. I'll just change it a little bit. Instead of IT as the output, sometimes somebody defines that I want VCT as the output. So you can say this is a second numerical or second modeling example. Question is, this second order RLC circuit, define it in state variable form, and YT is equal to VCT. Tell us what is the state variable model. This A and B will be same. There will no come any change if I am changing only YT. So defining IT as one state variable, defining VCT as another state variable. In that case, this A matrix, there will not be any change in that. Where the change will come? Just check that YT is equal to VCT, or I can write this equation as YT is equal to 0 or 1 of VCT, and there is no VT here, there is no input here. So this is just a representation issue. So the same thing, the C matrix, instead of 1 0, what I can write is, that's all. Okay, so I am defining now the output to be not IT, I am defining the output to be VCT. What I am defining is output is VCT, because again that output equation has to be given by the designer or paper setter. If instead of IT you are giving VCT as the output equation, in that case YT will 0 1 of this, because I am not changing state variables. Still IT and VCT are the variables which are defining the system. So instead of 1 0, because previous example this was the output equation, in this case VCT is the output equation. How to represent that? YT will be equal to 0 1 of this. If I am not changing the system, if I am not changing the circuit or mechanical system or thermal system, whatever is given here, if I am keeping the number of inputs same, in that case there will not be any change in A matrix and B matrix. It will be kept same. Only if I am changing the output parameter, then will change. Take the same circuit. Suppose somebody says I want VLT as the output. Just give a thought. I'll give you 2 minutes. What will be the output? So what you have to do is you have to represent YT as a function of IT, as a function of VCT, as a function of VT. So this is a numerical. I have changed output as VLT. So instead of IT or instead of VCT, what I am giving is this output is nothing but inductive voltage. So now this inductive voltage or YT I have to write in terms of IT, in terms of VCT. How can you write that? So this VLT or inductive voltage should be a function of IT, VCT and input voltage. Is it possible to write? Look at the circuit. Circuit is having total supply voltage as VT. This is equal to resistive voltage plus inductive voltage plus capacitive voltage. Okay. What I want is, I want VLT, that is inductive voltage. I want inductive voltage. Okay, this one. What is the inductive voltage? Inductive voltage is nothing but equal to input voltage, resistive voltage minus capacitive voltage. So this is very simple, nothing but addition of voltage, nothing but KVL you are writing. Okay. We are just having some technical difficulties. We will just pause this session, we will restart again. There are some streaming issues. We will just stop for 5 minutes and restart. visible. Sir, I'll check just. Let me check. It is possible. Visible. Visible. Here it is coming. Okay, welcome once again. Sorry for the unintended technical hitch in between. What we had been doing was I had been giving you the very simple model of state variable for a second order system. We have found the first equation very properly, that is I dot t and vc dot t, and I was just changing the yt equation. So initially we had taken yt as it, we got y matrix. Then I changed this yt as vct, I got y matrix as 0 1. Now I have changed the output equation as VLT, that is, this is the output voltage, is the what we want. In that case, how will the yt equation change? But for all these three cases, the first equation will remain same. So I was writing VLT in terms of the input and other voltages. So what we have found is VLT is equal to input voltage. Now we can change the input voltage, or I have written it in the right side. Input voltage is VT minus resistive voltage minus RIT minus capacitive voltage, and capacitive voltage we are giving as VCT. This equation of VLT can be written as VT minus RIT minus VCT. Now this equation can be written in terms of YT or in terms of CXT and DUT. So how can I write that? So YT is equal to this, we have to make the structure. So this is IT and this is VCT. The same state variables here will come here, okay, plus D matrix of UT. Now UT is nothing but VT. So what will be the C matrix now? So input, so this will be minus R, so minus R of IT. How much of VCT? Minus 1 of VCT. So this part now I am, and how much of VT? VT is nothing but 1. So just I have changed this output equation from IT to, now I am showing as VLT. So A matrix, B matrix will be same here. C matrix will be minus R minus 1 and D matrix will be 1. And A matrix and B matrix will be same as before. So this is 1 by L 0 and this will be, A matrix was equal to minus 1 by L 1 by C and this is 0. So if you want this system and this output, this A, B, C, D together, they are state variable modeling of the whole system. Okay, so this was the first modeling that we have done, and again we are finding that as 2 energy storing element, the order of the system is 2. This matrix will be having order of 2 by 2, and the coefficients are minus r by l, minus 1 by l, 1 by c, and 0. And there are 2 state variables. This will be 2 cross 1. So 2 cross 1 means 1 by l and 0. That means VCT is not having any bearing on VT, okay, but on VT. So that is what is done by this. Now C matrix, for this kind of output YT is equal to VLT, we are finding C matrix as minus R and minus 1, and D matrix is equal to 1. So dimension of D matrix is nothing but 1 cross 1, because there is only one input and only one output. So this was a very basic numerical. After this numerical, so many systems we have seen today, you try to develop your own state variable model for all the systems that was shown in last 2 days. It is all possible. Dimensional system, one dimensional system, A matrix will be a scalar, okay, and for 2 dimensional systems, A matrix will be a 2 by 2 kind of a thing. Next topic, transfer function finding, or find transfer function from state variable model. So now I will be giving you, and I'll ask you to find out what is the transfer function of the system. And if we know what is the transfer function of the system, the same thing, CT-LTI system, we can go and find what is the ODE for the system. Second task for today in state variable, that if ABCD matrix is given. So previous numerical, I had given you a system and you have to find out what are the ABCD matrix, or what is the state variable model. In the second case, if ABCD is given, so we will take a very simple numerical, smallest scale of numerical. We will take that the system. So you can start writing with me. X dot t is equal to, so this is a very standard numerical, x dot t is equal to 0 1 0 1 minus 2 and minus 3 of xt, okay, and plus B matrix is given by 0 1 ut 0 1 ut, okay, like this, and output matrix yt is given as 2 3 of xt 2 3 of xt, and D matrix is given as 5. Direct transmission matrix is given as like this. So this is another standard system where n is equal to 2, that is there are 2 state variables. This is a second order system, and those who want, they can write this xt as x1t and x2, so x1t and x2t. In the same way, this x dot t also can be written as in vector form, x1 dot t and x2 dot t, like this. So anything you write is correct, like this. So now A matrix is 0 1 minus 2 minus 3, B matrix is 0 1, C matrix is 2 3, and D matrix is 5. Supposed to find out is output Laplace divided by input Laplace. So the transfer function will be found in Laplace domain, and it is like this. What is the formula? So output Laplace by input Laplace, better we will call as HS. This is called as transfer function, like this, C into SI minus A inverse into B plus D. So this is the formula that we have to follow, okay. So how to find transfer function? Transfer function is nothing but C into A inverse into A inverse into B plus D. Now what is our A matrix, what is B matrix, what is C matrix? We will write here. So A matrix is 0 1 minus 2 minus 3, B matrix is 0 1, C matrix is 2 3, and D matrix is 5. Okay, so I need this board for calculating it. That's what I'm doing it again. So now I'll remove this equation because ABCD is written elsewhere. What we are supposed to find out is transfer function in S Laplace domain. What is the first thing? Finding SI minus A inverse, we will see. What is SI minus A? This is S. I is an identity matrix 1 0. So depending on the dimension of A matrix, we have to choose this I. So as A matrix is having dimension of 2 by 2, this I also will be identity matrix 2 by 2, and it will be S. If you put this S in between, this will become S0 0 S. Okay, minus A matrix is 0 1 minus 2 minus 3. So what is Si minus A? Si minus A we will find as S minus 0, this is S, 0 minus 1, this is minus 1, 0 minus 2, this is 2, and S minus of 3 plus 3, like this. So what do we find is Si minus A, this matrix is equal to S2 minus 1 and S plus. A very important step, finding Si minus A. While finding state transition matrix STM, also we have to do this step. So please understand, Si minus A we have to find. A is the system matrix. 2, I we have to choose as per the dimension of A. So this is Si minus A. So Si minus A is like this. Next step, find Si minus A. So first I told you how to find Si minus A, then find Si minus A inverse. What is the first step in finding Si minus A inverse is, first find how much is determinant. So S into S plus 3 minus 2 into minus 1, so minus of minus 2, so this is plus 2. So first step is finding determinant. So this is A square plus, that is equal to S plus 1 into S plus 2. So how to find Si minus A inverse? First step is equal to 1 by S plus 1, S plus 2, like this, and then just change it. So this will be S plus 3, this will be S, this will be 1, and this will be minus 2. So finding the second order inverse is very easy. So SA we had found, the Si minus A inverse is 1 by S plus 1, S plus 2 multiplied by S plus 3 minus 2, 1 and S. So this is our agenda. Please write down. So Si minus A inverse, that we have to find out. This is the answer. So first find Si minus A and then find the Laplace inverse. Inverse is having two steps. First find what is the determinant. Determinant is nothing but S into S plus 3 minus of plus of 2. So if you do the factorization, you will be finding S plus 1 and S plus 2, like this. And then how to find this changing? So you have to change this to position. So previously Si minus A was having S and S plus 3, I have changed this position, and this sign change you have to do. So previously it was minus 1 and 2, I have made it minus 2 and 1. So this is what is called as Si minus A inverse. What is the transfer function formula? Transfer function formula is C into Si minus A inverse into B plus D. So this is in one bracket. So now what is C matrix? HS is nothing but transfer function. C matrix is 2 and 3, and then Si minus A inverse. So first determinant S plus 1, S plus 2. Okay, so Si minus A inverse, this is S plus 3, this is minus 2, this is 1, and this is F plus 5. It is given here like this. Okay, so this part is Si minus A inverse. This is C matrix. This is Si minus A inverse into B. I'm sorry, I forgot the B part. So what is B matrix? B matrix is 0, 1 plus D. This is 5, like this. Okay, so this is minus A inverse into B plus D matrix is 5, like this. And now do the calculation, and the calculation I'll do in the left side. So this side and the calculation. So HS, which calculation to be done first? So just see that 0 and 1, if you are just multiplying 0 and 1, so this into 0, so this part goes and 1 remains, and this into 0 goes, so only we are getting the column number 2. So first do the multiplication of 0 and 1. So 2, 3. Okay, so first do this calculation. So this into this, so first we get as 1, and second is this into this, so then we get as, okay, so Si minus A inverse into B part we do first, and the C is there, and this is Si minus A inverse into B part, like this. Okay, plus D is 5. Then do this multiplication. So this multiplication will be, okay, something I have missed. So this is 1 by S plus 1, S plus 2, so this thing will be there. Okay, so this part is this thing will be here, it won't go anywhere. So it is like this. So denominator S plus 1, S plus 2, like this, and then 2 and 3s. So this will be 2 plus 3s and plus 5. So it's very simple multiplication. This is C into Si minus A inverse into B plus D. First we have taken care of this part, and we have got this as 1 and s, 1 by s plus 1 s plus 2, then multiply this, so this is 2 plus 3s, and this denominator is here plus 5. Okay, so s plus what, s square plus 3s plus 2. Okay. So now I'll remove this part, and hs equal to 2 or 3s plus 2 plus 5 into s square plus 3s s square plus 3s plus 2. So this will be, and denominator s square plus 3s plus 2. So this will be 5s square plus, so just do this, 5s square will come, so this is 15s and 3s, this is 18s plus this is 10 and 2, this is 12 divided by s square plus 3s plus 2. So this is going to be the hs. So simple. So this is 5s square plus 18s plus 12 divided by s square plus 3s plus 2. Okay. So this is a very simple step you have to follow. Only thing is, if it is 3 by 3 matrix, calculation of SI minus A inverse become little difficult. It becomes little big. That is the only difference. Otherwise, the steps are very simple. So C matrix will be given, A, B, D, all matrix will be given. Only calculation of S minus A inverse, that is the tricky part. Okay, and there we should be having a very clear-cut understanding of Laplace transform and partial fraction and all those things. If known very clearly, then only we can find SI minus A inverse very easily. And this SI minus A inverse itself is called as state transition matrix. Inverse Laplace transform of SI minus A inverse, that itself will be the state transition matrix. Okay, so that step again we have to do. So this is a very simple numerical which is saying if ABCD matrix are given, find the system transfer function. So we have found it. Take the next one, and if system transfer function is from ABCD matrix to system transfer function. Next is, if system transfer function is given, how back to ABCD matrix. So we'll take different numerical kind of a thing. We'll take a system which is called as y double dot t. So this is next modeling, what is called as I'll call as system function to schematic, system function to schematic to state variable to transfer function. So these are four things. What is called as system function, that means this is ODE. So this is the first thing, ODE. If ODE is given, I can go to the system block schematic. From block schematic I can matrix. So there is a third thing, and once ABCD matrix, I know what is going to be the system transfer function, like this. So system function and system transfer function, they are different. System function I am mentioning as the ODE, that is y double dot t plus something of yt or something like this. Okay. So let us have this numerical, solve this numerical in detail, and anything is given. If I give you state variable matrix and I ask you to find transfer function, we should be able to find. If I give you state variable, ask to find schematic, we should be able to find. So any of these four things are interchangeable or interoperable. Any of this thing is given and I can go and find the other thing. Okay. So let us take a very simple system equation ODE and find the other things. So it is given as y double dot t plus standard numerical we are solving, so that's why it's taking time. So like this, 2yt is equal to 4 x dot t plus xt. This is what it is. Okay. So this is the output side. This is d2yt dt2. This is 3 dyt dt. This is 2yt is equal to 4 dxt dt and xt. Any initial condition, how can we get the system transfer function? So directly we can find out with Laplace. You can find out this is ys if you are taking. So this becomes s square plus 3s plus 2 is equal to 4 or xs. This is 4s. So we can find hs. Hs is nothing but transfer function, that is xs or ys upon xs, that is output upon input. This comes to be s plus 1 divided by s square plus 3s plus 2, like this. So this is ODE to transfer function. So if some ordinary differential equation is given, how can I find transfer function? We are not considering any input conditions here, any initial conditions here. That's why directly in one step we have found out. Okay, so this is the starting point, system function to transfer function we have found. Now we will forget this system function, we will play with the transfer function itself. So what hs equal to 4s plus 1 and s square plus 3s plus 2. Question is find system schematic. So this will be find system schematic, or we can say that the technical block diagram of the system. Now from Laplace transform we call it realization. From Laplace transform you can find what is called as canonical form 1, you can find canonical form 2. So that is, so this system we can construct by using integrator, differentiator, amplifier, delay element and all. Once we construct the system schematic, from there we can find system state variable matrix. Okay, so first given is system equation ODE. From there we have found the system transfer function. From there we will find the to develop the system schematic from the system transfer function. That is the numerical we are going to do. I think question is clear. So from system function we have found what is called as system transfer function. From here find system schematic. So this requires little bit attention. So there will be a input xt and there will be a output yt. Draw first, and we find that this is a second order system. So whenever this is a second order system, we have to draw that there are two integrators. If this was a third order system, there had to be three integrators. As there are two second order system, there will be two integrators. And one more thing had to be given to you, that is output. So yt is equal to q, or yt is equal to state 1. This is the output. So state is generally given by q. So yt is equal to q1t. This is given. This is given. Somebody doesn't matter. It changes nothing, because I told you that we have to mention from the beginning what kind of output we want from the system. So whichever is the output state variable, or whichever is the output variable, that I am calling as a q1t. So state variable 1 and output, it has to be same every time. But for this kind of realization, this kind of circuit development, the output should be equal to q1t. So that is one restrictions, one limitation. Okay, so this is xt. So this is the input quantity and this is the output quantity. Now from here I will draw like this. So diagram will be same. Only thing is, depending on the transfer function, the coefficients will vary. So it is not here actually. I'm sorry, not here. This will be falling. So there is a adder here, and I'm sorry, there is a adder here, like this. Okay, and this adder is connected to this integrator, like this, and this thing will be having some amplifier thing. Okay. So this system is different from other system. Only there are 4 coefficients. This is 4, 1, 2, 3. These 4 things we have to incorporate in this system. Okay. So how to incorporate this system? So this 4s plus 1. If this is 4s plus 1, this is an amplifier, and this will be having a gain of 4. This is an amplifier, this will be having a gain of 1. So this is how to draw it. Okay. So how did I draw it? So first I took xt, then I took yt, and it is like this. And here from xt there comes an amplifier comes to an adder, and adder comes to a integrator. So from this, if this is 4s plus 1, so whichever is the power of s, that will be written in the left side. Whichever is having higher power of s, that will be written in the right side. So if this is 4s plus 1, that means this will be 4 and this will be 1. So this is canonical form 2. Compensate for this. So first thing, we have to make this highest term of s coefficient as 1. That is something we have to do. Okay, so that is already done, so nothing to worry. So now 3s plus 2, how to draw it? Now, so from this output there will be some kind of input thing, okay, like this, and here it will come to the another amplifier. So there is a feedback kind of thing. So this is the feedback path, and from here again this, and as this is negative feedback, here it will be minus, here it will be minus. So this 3 comes here and this 2 comes here, like this. So this is the system. This is the system schematic what we have found from the transfer function, and this is called as number 2. In canonical form 2, what we are finding is we want only one integrator. So this is the output side and this is the input side. So input side and output side both are there and same set of integrator. So how to represent this system in one form, 4s plus 1 and s square plus 3s plus 2. This thing is called as realization. Canonical form 2, realization for the given system. So how to do it again? So this is hs is nothing but ys by xs. So these are the coefficient related to xs. So 4s plus 1 is related to xs. So this 4 should be taken here, 1 should be taken here. 3s plus 2, this coefficient has to be made equal to 1. So 2 will come here, 3 will come here. This should be negative and this should be negative because we are configuring the whole system into negative feedback configuration. Now this thing has to be q1t. Automatically it comes because output equation is given yt is equal to q1t. So whatever is being generated at the output, that same thing is nothing but yt. So q1t. Some quantity is there, it is integrated and we are getting q1t. So what will be this? This will be q1 dot t. Okay. So integration of differentiation comes to be the same factor. So x1 dot t integration comes to be x1t. Same thing, q1t is the integrated output of q1 dot t. What is q1 and q2? They are nothing but what here directly you can write this is q2t and this will be q1 dot t like this. So at this point whatever is the signal coming, that is called as q1 dot t, getting integrated, this is at this point q2t. Whatever is that output, that is called as q1t and that is integrated form of q1 dot t. So this q1 dot t is equal to q1 dot t is integrated and q1t produced, q2 dot t is integrated and q2 is produced. So up till this point if it is okay, then we can go forward. And we have to now write two equations. We have to write the equation of q1 dot t and we have to write the equation of q2 dot t because we are in a process of developing state variable system from the transfer function. So from transfer kind of system. Okay. Now how to write key that q1 dot t is the signal at this point and that is nothing but addition of three signals. Which are the three signals? First one is q2t. So q2t is coming from here, 4 of xt direction. So directions also we should show like this and like this. So all the directions is shown. So how to write the q1 dot t equation? So q1 dot t is nothing. First I'll write so this equation is q1t, just say that this is q1t is coming and q1t with 3. So this is minus 3 of q1t. Okay, this q1t is coming from here 3 and this thing is minus 3 q1t. This thing is the signal is 4 of xt and this is q2t. So this q1 dot t here is coming minus 3 q1t plus 4 plus q2t plus 4 xt like this. Okay. So q1 dot is 4 xt plus q2t. How can I write q1 dot t? So this is I'm sorry, this should be q2 dot, this should be q2 dot t because q1 t is here, q1 dot t, this is q2 t and this is q2 dot t. Okay, so this is q1 dot t I'm writing. How to write q2 dot t? So q2 dot t is nothing but addition of xt and yt. So you can write down that this is how much of xt? So this is 1 into xt, 2 into q1t like this. So this q1t is coming here, also it is q1t going. So this is minus 2 q1t like this. So this minus 2 q1t is coming from bottom and 1 of xt is coming from top. So q2 dot t is equal to 1 xt minus 2 q1t. Is there any q2 function here? No q2t like this. Okay. So there is no q2 function here, that's why this will be 0 q2t. So now see that we have got equations of q1 dot t, we have got equation of q2 dot t. What is q1 and q2 are nothing but the state variables. So how have we defined this? This has been defined just like that. This has been defined just like that. So this line will always be like this. T will be corresponding to q1t. Then there will come a integrator. Then before integrator, if this is q1t, this will become q1 dot t. Then again before this summer there will be a q2t. There is an integrator, and after this, before this, there will be q2. There is a summer. If there is another thing, integrator, here it will be q3 t, and then integrator. Then before this integrator, it will be q3 dot t, and it will keep on going like this. Okay. So from this schematic, we have found three equations: minus 3 q1t plus q2t plus 4xt. That is nothing but equal to q1 dot t. And qt, that is 1 of xt, is nothing but xt, and minus 2 q1t and 0 q2t. Now I'll remove this because job of schematic is done. So from system ODE we had come to function, from transfer function we have come to schematic, and from schematic we have written these two equations. Now write state variable matrix. So q1 dot t and q2 dot t. How can we write this thing in terms of q1t and q2t? And then there will be B matrix and there will be xt. And what is yt? Yt, I told you, output. So output is nothing but function of q1t and q2t like this, plus something of xt. So this is A matrix, this is B matrix, this is D matrix. How can I get the A matrix? So just check. q1 dot t is equal to how much of q1t? So this is minus 3. Okay. So q1 dot t is equal to minus 3 q1t. How much of q2t? q2t is 1. How much of q3t? There is no q3, but how much of xt? So this will be 4. So this is the first equation, that is q1 dot t. How did we get the q1 dot t? q1 dot t was taken from the so this is minus 3 q1t plus q2t plus 4xt. So this top is the first equation. What is the second equation? So q2 dot t, this is equal to minus 2 of q1, and there is no q2 function, so this will be 0 q2t and 1 of xt. So what is A matrix? A matrix is minus 3 1 minus 2 0. And what is B matrix? B matrix is nothing but 4 and 1. How much is the C matrix? If you see your block schematic, q1t is equal to yt. So yt is equal to q1t, that means 1 and 0. And there is no direct transmission. Input and output, they are not directly connected. No direct transmission. That means this matrix will be 0. So just check this two equation. So this is like this. So this is q1 dot t and q2 dot t. We have found these two equations out from this. And here we have found it minus 3 q1t. So this is minus 3 is here. This is q2t. This is q2 here. And this is 4xt. The 4 is here. For q2 dot, it is 1xt minus 2 q1t. So this 1 comes here, and this is minus 2, and there is no q2. So q2 is 0. And this thing is given. So what I'll write is, from system function we found the transfer function. From transfer function we went to schematic, and from schematic we have found the static. A matrix is minus 3 1 minus 2 0. B matrix is 4 1. C matrix is 1 0 is 0, like this. So 4 things have been found so far: system function, to transfer function, this is the second thing, to block schematic, to state variable. What is the last thing? If this is the state variable given, can we get the same transfer function? So we have to come back again to the same point to complete the loop. Transfer function is 4s plus 1 a square plus 3s plus 2. Okay. Does this thing give us the same transfer function? If it does give, that means whatever formulation we have done, that formulation is exactly correct. So let us have a cross check. That is, this ABCD matrix, whether giving me the same transfer function or not. What is the formula? So HS equal to transfer function C into SI minus A inverse into B plus D. Okay. So now forget this above part. Now just see this: A matrix, B matrix, C matrix is given in transfer function. So what is C? So now HS is equal to C. C is nothing but 1 0. Okay. What is SI minus A? So let us solve it first. So Si minus A, this becomes S plus 3, and change the sign, this becomes minus 2 and 1. So this is actually Si minus A inverse. So Si minus A inverse is nothing but inverse of Si minus A. It comes like this. So C into Si minus A inverse. So C into 1 by S plus 1, S plus 2, like this, and this is S 1 minus 2 and S plus 3 into B. How much is the B matrix? B matrix is 4 and 1, and D matrix is 0. So plus, so multiply this. Okay. So for multiplication, what we can do is we can take S plus 1 and S plus 2 in beforehand. Multiply this thing first, 1 0 with this. So if you are multiplying 2 cross 1 and with 2 cross 2, what you will get is 2 cross 2. So fine, just multiply this. So this with S like this, and this with 0. This is gone. So this S I will write here. Okay. So 1 into S plus 2 into 0 gone, and this is 1 into 1 and 0 into this. So this will be 1 like this, and this is 4 1 and D matrix. So see that denominator is same, that is S square plus 3S plus 2, and numerator is 4S plus 1. So again, whatever transfer function we had started from, again we have come back to the same transfer function. That means whatever state variable we have defined, that has been defined very correctly. So these things we have to keep in mind, that is system function is given in ODE. From there we can find out what is the system transfer function. So system function to system transfer function, first step. System transfer function to canonical form 2, system schematic. Now a lot of people exactly don't know how to define state variable initially. You won't have to define the state variable. What you have to do is, if system function is given, come to system transfer function. Once you come to schematic, in the schematic, in the middle line, that middle line is q1t, q1 dot t, q2t, q2 dot t. So just write to the middle line of the canonical form 2 block schematic, and from there you will be able to write what is the q1 dot t and q2 dot t state variable equations. From those two equations you can again formulate what is A, B, C, D matrix. As there is no direct transmission, D matrix in this case is 0. And once you are having A, B, C, D matrix, from there again you can find what is the transfer function, an initial transfer function, and this transfer function you can check. And so this is a big loop. Anything given to you, you can go to the other. So 5 things we have to remember: system function, transfer function, schematic, state variable, and again come back to transfer function. So this loop, anywhere I ask you a question, we should be able to answer the other. Okay. So this was the first part of the lecture. The second part of the lecture is mainly with solution of state variable model, related to how to develop a state variable model, that is how to develop the ABCD matrix and what are the characteristics of state variable matrix. So this thing is done. Next part is how to solve the variable matrix. So to solve the state variable matrix and to solve the whole equation, what we are supposed to do is we are supposed to find what is called as state transition matrix. Already we have started finding it. So this is called state transition matrix, or in short it is called STM. So now I am solution of state variable system model. So this is the second part. We are going a little delayed. I don't think this will be completed by 1. So I'll be extending it to some 15-20 minutes or so. Okay, at least a small part of it I'll be able to tell how to solve this equation. So I'll be extending this session for around minutes. Possible? There is no technical glitch, right? Okay. So how to solve the state variable model. Now the problem is, if I give a MIMO system, if I give a 5 by 5 system, or if there are 5 state variable or 5 variables in the system, I have to get the time domain equation of all 5. That was not possible by the ODE based system or transfer function based modeling that we have seen till yesterday. So for multi input multi output system, solution finding was not possible by the simple system or simple method or transfer function based method yesterday. So for solving a multi input multi output system, to get the state equations, all state equations together, it was not possible by transfer function based system. That is possible by this system, that is possible by state variable method. And how to get that? The first thing is we are supposed to find out what is called as state transition matrix. So I will be solving a homogeneous system, I will be solving a non-homogeneous system. Let us first start with solution of a homogeneous system. So write down the equation or system is same. So we are going to find out for A is equal to, so I am giving you first a model, and then question is solve this model. So what is meant by solve is we are supposed to find out state variable equations in time domain. So this is -2 and -3. So A matrix is given. Okay, A matrix is given, and I am asking you to find what is called as state transition matrix. And why am I finding state transition matrix? Because state transition matrix is the first step of solution of the system. What is meant by solution of the system? So if there are two variables, this is a 2 cross 2, that means n is equal to 2, that means there are two state variables. I can find out the equation of q1t and I can find out the equation of q2t in time domain. This is what is meant by solution of SVM. So exactly what is the solution? Solution is this. I am having the A matrix. From A matrix I will calculate what is called as state transition matrix, and for homogeneous system and for non-homogeneous system I should be able to find out what is the equation of q1t and what is the equation of q2t. I am not giving here B matrix, C matrix, D matrix, all those things are required, but let us first find how to find state transition matrix. Already we have found it. Let us see. E raised to at is called as state transition matrix, is equal to inverse Laplace transform of Si minus A inverse. That's it. For two cases we have already found what is the Si minus A inverse. Once minus A inverse, just take inverse Laplace transform of that, and that is nothing but state transition matrix, which is called as e raised to at. What is the significance of e raised to at? State matrix. So if I know that, just giving an example, if I know that some current graph is like this, okay, so at t is equal to 0 it is starting from 5 e raised to -2t, okay, like this is 1, let's say, okay, this is a graph, this is t. After every time, after every instant of time where the b, what will be the state of the graph, this state change is captured by state transition matrix. So in state transition matrix I'll put t is equal to 0, I'll give this value. In state transition matrix I'll put t is equal to 1, then it will give me what is the amplitude at e raised to -2t at t is equal to 1. So state transition matrix is capturing that dynamics with which the parameters are changing its amplitude to time. Okay, so that's why finding state transition matrix is very much important, and this is the only thing which is little complicated looking, is not complicated. Okay, so let us find out that. We have already done the first part. So Si minus A inverse, A is given. What is Si minus A? So that we have to find first. So this is S minus 1, 2 and S plus 3. The same numerical we are doing. Okay, what is Si minus A inverse? Si minus A inverse 1 by, so S square plus 3S plus 2, that means this is S plus 1, S plus 2, and take it, so this is S plus 3, 1 minus 2 and S. So this is what is called as Si minus A inverse, like this. Okay, this is what is called as Si minus A inverse. And how to find e raised to at? E raised to at or state transition matrix is nothing but inverse Laplace transform of Si minus A inverse. Let us first streamline what is called as Si minus A inverse. So Si minus A inverse, Si minus A inverse. Now let us just multiply these two. So what we are finding is this is S plus 3 into S plus 1. Okay, so the determinant we are trying to push inside the system. So this is 1 by S plus 1, S plus 2, like this, and then this is minus 2 by S plus 1 and S plus 2, and last is S by S plus 2, like this. Okay, so again let's have a recap. A matrix is given, Si minus A we have found, Si minus A inverse we have found. Once we have found Si minus A inverse, this whole factor has to be taken into time domain, and Si minus A inverse, inverse Laplace of Si minus A inverse is state transition matrix or e raised to at, which is capturing the dynamics of variable change with respect to time. Now I have taken all this SI minus A inverse thing. Now this solution is required. Okay. Now only thing where we are stuck is we have to do 4 partial fractions. Okay. If you are doing four partial fractions, what we are finding is ILT of SI minus. So we have to do is ILT of SI minus A inverse. That means ILT of the whole thing. Okay. So this is a 2 by 2 matrix, and I'll not waste much time on partial fraction because we know this. Let me check it, and let me give you the values. So this is s plus 3 1 minus 2. Directly write down. So this is 2 by s plus 1 minus 1 by s plus 2. Okay. So this is the first term after partial fraction. This is 1 by s plus 1. It doesn't take much time to do partial fractions. Calculator is also having the function in it. So minus 1 by s plus 2, like this. Okay. And what is the next thing? 2 by s plus 2 minus 2 by s plus 1, and last thing, this is 2 by s plus 2 minus 1 by s plus 1. That's it. Okay. So here this is SI minus A inverse. This is in compact form, and we are finding what is called as the partial fraction of each of these things, and we have got the partial fraction. Now the last step, ILT of this part. So e raised to at is equal to ILT of SI minus A inverse is equal to. So this will be a 2 by 2 dimensional e raised to at, that is for 2 state variables. The dimension of e raised to at also will be 2 by 2. How to find it? So this 2 by s plus 1 means 2 e raised to minus t, inverse Laplace transform minus e raised to minus 2t. This is 2 into e raised to minus 2t minus 2 e raised to minus t. Here it is 1 by s plus 1. That means this is e raised to minus t minus e raised to minus 2t. And lastly 2 by s plus 2. So 2 e raised to minus 2t minus e raised to minus t. So this is what is called as state transition matrix, and this is how to find it. So step is first find SI minus A, then find SI minus A inverse, take the determinant into the brackets or into the matrix, perform the partial fraction, and after partial fraction you can get what is this thing. So this is the first term, this is the second term, this is the third term, and this is the fourth term, like this. Okay. So this is let me confirm. So 2 e raised to minus t minus e raised to minus 2t, then e raised to minus t minus e raised to minus 2t, 2 e raised to minus 2t minus 2 e raised to minus t. Last term is 2 e raised to minus 2t minus e raised to minus t. That's it. Okay. So this is how to find the state variable or state transition matrix for any A matrix which is given to us. So I'll just write down, this is e raised to at is equal to state transition matrix is equal to like this. Okay. Why state transition matrix is required? That is, topic is solution of condition, because solution of state variable requires what is the initial condition of the matrix. So this x is nothing but state variable. In this case, as there are 2 state variables, what is there? This is x1 or x10, and this is x20, like this. So this initial condition for both the state variable quantities should be given to us. Without that, this solution is not possible. So please take a numerical, keep this e raised to at as same. Take a numerical, that is solution of homogeneous state variable model. Solution of homogeneous SVM. Okay, homogeneous SVM. What is meant by homogeneous SVM? X dot t is equal to axt. This is a homogeneous system. This but not there, and yt is equal to cxt. That's all. So this is the SVM for a homogeneous system. Yesterday also we have done that hydraulic system model with external input and without external input. So first we start with homogeneous system modeling. What is homogeneous system modeling? that ut part is not there. So what is x dot t? X dot t is nothing but q1 dot t, q2 dot t. What is xt? Xt is nothing but q1 t, q2 t. Okay, this is more compact form. Yt is output. Output is only one. That is equal to c of xt. This xt is also q1 t, q2 t. So if this is the system, that is x dot t is equal to axt, where a, b, c matrix are given like this. Find the solution of the system. What is meant by finding solution of the system? Finding solution of the system is nothing but you have to find out what is the q1t equation and what is the q2t equation in time domain. So same as solution of ODE that we have done, here also we are doing the solution of ODE, but not in simple algebraic form, but in a compact matrix based form or subspace based form. That's why this is called solution of SVM, not solution of ODE. Okay, how to find the solution? So x dot t is equal to axt, yt is equal to cxt. What is the solution? So this is a homogeneous system. Homogeneous system solution is given by, so we can write down solution is given by xt is equal to e raised to at into x0. That's it. Okay. So this is the system. X dot t is equal to axt. Dimension of xt here is 2 cross 1 because it's a two variable system. Dimension of x dot t is also 2 cross 1. In that case, e raised to at we have found, the same e raised to at is found for 0, 1, minus 2, minus 3. So this A matrix, whatever is given here, is nothing but 0, 1, minus 2, minus 3. How to find the solution of that? So to find the solution of the system of homogeneous system, xt, that is the state variable. How to find the xt? Xt is nothing but x1t and x2t. Okay, what is x0? X0 is nothing but x10 and x20, and this should be given. This should be given. Without this thing given, we cannot find it. And if it's an initially relaxed system, there is no initial condition, that means x1t, x2t will be all equal to 0. Okay. So as it is given here, you can find x0 is the initial condition. And what is the initial condition? We can take initial condition the way we want. So you can take initial condition as 0, 0, you can take initial condition as 1, 0, 1, 1, 2, 5, 7, 3, anything. So you can assume just for the sake of assumptions. So what is the initial condition? Let us take initial condition is equal to 2 and 3. Let us take. So x0 is equal to 2 and 3. That is x10 and x20, like this. Okay, just like this. In that case, what will be the system? If I take initial condition as 1, 0, then what will be the output? So it is like this. So we can take initial condition as 1, 0 also as well, like this problem. So what is the solution? Solution is nothing but x1t, x2t raised to at into initial condition. So what is initial condition? 1 and 0. So we have found already e raised to at. So what is the solution now? Now I am finding solution. So solution is nothing but xt. Xt is equal to e raised to at multiplied by x0, like this. So this is e raised to at and this is x0, and this is the solution. And what is meant by xt? Xt is nothing but x1t and x2t, like this. Okay, now do the multiplication and find what is the answer. So from the beginning, if I want to give a recap, that homogeneous system is there. Homogeneous system is given by x dot t. X dot t is equal to axt, like this, and yt is equal to cxt. There is no ut term, there is no forcing functions, there is no external input. In that case, how can I find the system response? So this is kind of a zero input response of the system that we are finding, because zero state response is not there, because there is no ut term. So we are only supposed to find out the zero input response of the given system. So if this is the system, we want only A matrix to find out what is the state transition matrix. So first step is find e raised to at, and second step is multiply x0 with that, and that is the system solution. So first step, I have found out state transition matrix, and second step, x0 is given as 1, 0. So I am multiplying e raised to at with x0, and I am getting what is the solution. So what is the solution now? x1t, x2t. So just do this multiplication, and you can see that this multiplied by this and this multiplied by this. That means only this term is existing, and this and this. So this first term is existing and second term is not. So if you are multiplying this thing, only the first column will exist. So what is the solution of the system? x1t, x2t. Solution is nothing but 2 e raised to minus t. So this is the first column, minus e raised to minus 2t, and this is 2 e raised to minus 2t and minus 2 e raised to minus t. That's all. So only the first column is existing. If you are multiplying this with this, we will be getting only the first term. Then next job, we are supposed to plot it. So if you are plotting it, what you will be finding is this x1t, x1t. Okay, so x1t plot will come somewhat like this. So we have done it by MATLAB. So around 5 seconds or so, it will start from some value. I'm having all the values with me. So let me just find and tell you. So the graphs are like this. This is the first graph. It will start from 1 and somewhere around 5, 6, so around 5 seconds it will come to 0. So this is the graph of x1t. So what is x1t? x1t is nothing but this graph, 2 e raised to minus t minus e raised to minus 2t. What is going to be the second graph? x2t. x2t, so you can plot it very simply by using MATLAB. So x2t is like this. It will start from 0. Okay, so this will be a negative graph. This will start from 0 and this will fall somewhat like this, and then it will go and asymptotically it will reach 0, and this time is around 0.7 seconds and this height is around minus 0.5. It's like this. So this is the graph of x2t. It initially falls very fast, so this is the transient region, and then it asymptotically increases and it goes towards the 0 amplitude. So this is 5 seconds like this. So this automatically decreases. So this is the first graph. So this is the second graph and this is the first graph. It is like this. Okay. Now if I give you 10 inputs, your A matrix will be 10 by 10. Then 10 input conditions has to be given here, and after you find e raised to at of 10 by 10, multiply this 10 by 10 with x0 with a 10 cross 1 matrix, and you will be getting 10 functions like this, and by very simply using MATLAB you can plot all these 10 state variables in the one shot very easily. Okay, so this is what is the significance of state variable. So from very simply whatever system we had given, that is system function, that is y double dot t or y triple dot t, something like that, ODE equation. From ODE equation you have to come to state variable. Once you come to state variable, you have to find what is state transition matrix, multiply the state transition matrix with the initial conditions, and that is giving you the solution for homogeneous system. Last topic and most big topic, but I have taken a very small equation for that. Non-homogeneous system. Steps are same, only the formula is little big, but I have taken a very small numerical to show you that. So this is the last topic for SVM, that is solution of non-homogeneous system. Solution of non-homogeneous state variable system, variable model. Okay. Let us take this like this. So given x1t and x2t are two state variables. So x1 dot t x2 dot t are given, and system matrix is given as a diagonal matrix. So this is minus 1 0 and 0 minus 2, and this is x1t, this is x2t plus B matrix and ut like this, and this is given as 1 1. So B matrix is very important, A matrix, B matrix. You can check that for solution of state variable for homogeneous system we required only A matrix. Matrix, D matrix, B matrix, they were not having any bearing. Anyway, for homogeneous system B and D matrix are not present. Okay, but for this matrix also are C or D matrix. For homogeneous system B was not there. For non-homogeneous system C and D are not required. So if you are having only A and B matrix, we can find out what is the final output or what is the solution of this system equation. So what is meant by solution? Solution is nothing but we have to find the equation of x1t and x2t. We are calling this as xt. This is a formula. xt is equal to e raised to at into x0. Okay, so what we find is in non-homogeneous system there is a homogeneous part. What is this part? This part is nothing but given by initial condition. This part is nothing but given by this is a zero input response. So what we have just now found here in the previous homogeneous system, this is nothing but zero input response. But as non-homogeneous system is having a next part, what is the next part? There is a B matrix and there is an input. So this input also has to be mentioned. Let us take in this case input is step input. What is meant by step input? Laplace 1 by s. Okay, unit step input. Let's take this is unit step input. Unit step input means ut amplitude is 1 and ut is us is 1 by s, like this. Okay, so this is the system. This is the system, and forcing function is as 1 and 1, and forcing function is nothing but unit step input. What will be the state variable or two state variable equations for this system? That we are supposed to find out. So x1t and x2t we are supposed to find out. So first part we are getting e raised to at into x0. Second part is little tricky. So it is kind of a convolution, kind of 0 to t e raised to a t minus tau and then b u tau d tau. Okay, so this is actually response for forcing function. Response for forcing function is equal to 0 state response. Please write it down. This thing is like this. Okay, so this is the initial part. So this is the non-homogeneous system. This is the initial part e raised to at x0, and this is the forcing function part, or this part is the response for whatever input is given to it. So now input is given is unit step input, and for this how to calculate the whole thing, that is the thing to be shown. Solution we will do in 4 and 5 steps, and that will be it for the day. Okay, so this is the thing, and we are supposed to find out. So directly I will give you what is the state transition matrix of the system. It has to be found in the same way. So just write down the formula, problem formulation, that is x1 dot t, x2 dot t is given by A and B matrix. Input is given as 1 by s or unit step. One more thing is required, that is x0. So you can write down that x0 is given, dimension of x0 is 2 and 1, x0 is given as 1 0. Okay, so this is a input condition given, this is a input condition given, and this is a input condition given, and B matrix is also an input condition given. So with all this we are supposed to find out the solution of this non-homogeneous system and how to find the solution. So let us solve this. Xt is x1t, x2t, e raised to at. So e raised to at I will give you. E raised to at is simply here as this diagonal matrix. This is e raised to minus t 0 0 e raised to minus 2t. Okay. So for this thing, for this a you can find by the same method. E raised to at will be 0 0 and e raised to minus 2t. So e raised to minus t and x0. This is 1 0 plus. So this is the zero input response part. So this is zero input response part. If you multiply this with this, so this was the only solution for the homogeneous system equation plus this part. Now this part is a little difficult. Let us draw 0 to t e raised to a t minus tau. Okay, so whatever e raised to at is there, instead of t you are supposed to write t minus tau. Okay, so here for this t is not a variable. For this integration variable is tau. So just write down this e raised to a t minus tau in 2 by 2 form. So instead of t just write t minus tau. So this is e raised to t minus tau. Okay, then 0 and 0 e raised to minus 2 t minus tau. That's it. Okay, so this is e raised to a t minus. What is the value of b? B is nothing but given, B is nothing but B matrix, that is 1 and 1, it is given. Okay, u tau is nothing but ut or u tau, amplitude remains same. Okay, so the amplitude is 1 and d tau. So this is the first thing, e raised to a t minus tau. So instead of t, just substitute time t minus tau. This is a B matrix, and this is u tau, the amplitude, and this is B, and this is e raised to a t minus tau, and d tau is there for integration. Okay. Now this thing we can solve very easily. This multiplied by this 0 and this. So if we are multiplying this, finally we will be getting only this part. Okay. Finally we will be getting only this part plus. Now if you multiply this thing, okay, we'll be getting some different things. So this is 2 by 1, and this is 2 by 2, and this is 2 by 1. So if we multiply this, it will be something different. Okay. So do the multiplication, and let us find out what is going to be the answer. So here it is 2 cross 1 like this. Let us find out. So multiply this with this. So it will be a 2-dimensional thing. So 0 to 2, 0 to t. So this into this. So this is e raised to minus t minus tau. That is the first part. This into this, and second part this into this. So what remains here is e raised to minus 2 t minus tau. Okay. I'll just remove this. If you are multiplying a t minus tau with a and 1, what remains is only this first part. So this much part we should put in a bracket, and I know the time is extended. Please bear another 5 minutes with me, and we'll be done. Okay, like this, and this is d tau. So here is the crunch thing that generally is not understood very easily. This is e raised to minus t and 0 plus integration of 0 to t. So the limit is given as 0 to t. So that means t is not the variable here, tau is the variable. How do we do this? So this is e raised to minus t into e raised to tau and d tau. And here it is e raised to minus 2t into e raised to 2 tau d tau. So these are the two integrations that we are supposed to solve. So instead of one, we are supposed to solve this two integrations. Okay. So I have just opened the bracket. So this is e raised to minus t, e raised to tau, and e raised to minus 2t and e raised to 2 tau. So I will not be coming this side here. So this is e raised to minus t 0 plus. How much is going to be this integration? So first I will take e raised to minus t outside and e raised to tau. What is the integration of e raised to tau? Again the same thing, e raised to tau. And then take this thing inside. Okay. So this is e raised to tau with t. So this is e raised to t minus e raised to tau with tau is equal to 0 minus 1. So this is the first thing. And what is the second thing? Second thing is e raised to minus 2t is outside. Okay. Now e raised to 2 tau. What is the integration of e raised to 2 tau? Half. So that half comes here. So that half I will take here, e raised to minus 2t like this. Then this is e raised to 2 tau. E raised to 2 tau with t. So this is e raised to 2t minus e raised to 0. Now e raised to 0 is nothing but 1 like this. Okay. So we are almost toward the end. Okay. So this is the system given. This is the system given, and initial condition is also given. Initial condition is 1 0. This already we have used. Okay. Unit step input is given, that already we have used, and what we are finding is xt. Okay. What we are finding is xt is nothing but this xt is nothing but this. So that is x1t and x2t. Two more lines. Last line, x1t is equal to. So what is x1t? This plus this. So this is e raised to minus t plus of. Okay. If you are multiplying this two, it is 1. So that is plus 1. And if you are multiplying these two, it is minus e raised to minus t like this. And see, e raised to plus t and e raised to minus t, plus and minus, minus t, they get cancelled. So x1t is equal to 1. So what we find is the first state variable is a DC quantity. So there is no time parameter in the first state variable. What is x2t? X2t is, we have to see, so this is 0 plus this part. So half of half of e raised to minus 2t and e raised to 2t. So this is 1, 1, and this goes inside, so minus e raised to minus 2t. So how much is this? This is equal to half of 1 minus e raised to minus 2t. So this is equal to x2t. So these are solutions. So non-homogeneous system is given with step input, and we have found the solution. x1t is equal to 1, which is a DC quantity, and x2t is equal to half of 1 minus e raised to minus 2t, like this. And you can plot this. I have the values, okay, for this thing. So this is a DC graph like this of amplitude 1. For this thing, at t is equal to 0, x2t is equal to 0. For t is equal to 1, this is 0.4323. For t is equal to 2, this is 0.49. For t is equal to 3, this x23 is, so this is is equal to 0.4987, and for t is equal to 5, 0.4999, like this. So it gets saturated at 0.5. So if we are plotting this x1t and x2t, what we find is, so this is a plot for x1t, so this is t. The plots you can do very easily by using MATLAB, and for this plot x2t, so this is t, this is x2t. So at t is equal to 0, if you substitute t is equal to 0, that means this part becomes 1. So 1 minus 0, so it starts from here. Okay, exactly the dynamics of the second order system that we had seen. So it will start here and will go like this, where input is 1 and this is around 0.5. So this is the dynamics of x2t. So this is solution number 1, state variable 1, and this is state variable 2. Okay. So these are the things that I had to explain today. So I'll sum up. We had started this session with state variable model. State variable model. What is the necessity of state variable model? So what we have found is state variable modeling is a lot better than this transfer function based modeling. There are mainly 3 aspects. First aspect is if there are intermediate systems, if the total system is interconnection of many systems connected in cascade, then for that kind of system, if you are using transfer function based modeling, we cannot get the intermediate intricate details. Okay, but for state variable system model, we can get the internal details of the system much more easily, because we are tracking the states at every time instant. Now we have found this state transition matrix. In state transition matrix, we can set the step as 0.01 also. So we have found e raised to at. What is the value of t that we decide? How do we find this graph? In state transition matrix only, we are setting the value of t as 0, 1, 2, 3 and all, and we are getting what is the next value of the state. So that timing step we can set as less as possible. So at every very small timing detail, how much is going to be the variable amplitude, how the variable is going to change after every small time, even that minute detail can be picked up by this state variable system modeling. Okay, so that is the first thing, that is transfer function based system cannot give us intricate internal details, but state variable system modeling gives us what are the intricate internal details. Second thing, transfer function based system mainly cannot take initial conditions into it. So it's a very kind of a coarse kind of modeling, it is not very fine modeling. But state variable system modeling, we have seen in this case also, we have taken into consideration how much is the internal or initial conditions, and we have incorporated that in both homogeneous system solution and non-homogeneous system solution. So internal initial conditions can be considered in case of state variable system modeling. Third, which one is very important point, that is transfer function based system cannot handle nonlinear systems, it cannot handle time varying systems. But state variable system modeling, I will just give you a small glimpse of it. Whatever we have written, that is x dot t is equal to axt plus but, and yt is equal to cxt plus dut. So this is the state variable model for time invariant system. If the system is time variant system, in that case this A matrix becomes AT, B matrix become BT, C matrix becomes CT, and D matrix becomes DT. In that case, this becomes state variable model for time varying system. In that case, that model ABCD, it's a function of time. Okay, so in that case, the system becomes overall time varying system. A becomes AT, B becomes BT, CT and DT, and accordingly. Okay, so this state variable system modeling can handle nonlinear system as well as it can handle time varying system, whereas transfer function based system can only handle linear and time invariant system. So these are the advantages of state variable system modeling. Then from there, we had taken the example of linear system, that is RLC series circuit, and we have developed what is A matrix, which is called as system matrix, B matrix input matrix, C matrix output matrix, and D matrix what is called as direct transmission matrix. Okay, so dimension of A is 2 by 2. If n is equal to 2, there are two state variables, and state variables are found exactly equal to the dimension of the system. Dimension of the system is equal to number of energy storing element in the system. Okay, so B matrix dimension is n cross input. So if there are two inputs and there are two state variables and one input, this will be 2 cross 1. Y matrix, Y is given by CT xt. What is C matrix dimension? It is output cross state variable. So if there are two state variables and one output, this will be 1 cross 2. And finally, D matrix, it is input cross output. So if there is one input, one output, it will be 1 cross 1. We have not seen the block representation of standard state variable system, but we have seen the block representation of a numerical taken. So after that, what we did was we found out what is the transfer function from state variable model. Then we had given a ODE, as two-dimensional ODE. From there we found transfer function. From transfer function we generated second order canonical representation of the system. Again, from canonical representation we found what is the state variable model, and after we found the state variable model, from there again we cross checked the transfer function. So it was there. So this was the first part of the system. Second part of state variable modeling was solution of state variable model. So for finding solution, first we are supposed to find out state transition matrix e raised to capital AT. That is nothing but equal to SI minus A inverse and inverse Laplace of that. So SI minus A inverse is called as phi s. It is like this. Phi s is SI minus A inverse, and inverse Laplace transform of that is equal to phi t is equal to e raised to AT is equal to state transition matrix, like this. And this state transition matrix is the first thing we are supposed to find out if we want to find the solution of any given system. Now there are two systems we have attacked. First system was homogeneous system where there was no input, and solution of that thing was e raised to AT into x0. This is the solution of xt for homogeneous system. This is homogeneous system. And if it is non-homogeneous system, then e raised to AT into x0 plus 1, this is 0 input response, and this is 0 input response, and this is 0 state response. So this is A of t minus tau, B is the input matrix, u tau and d tau, and this is going to be a matrix form. So if it's a 2 by 2, A matrix is a 2 by 2 matrix, then this will be 2 cross 1, that is 2 row 1 column thing. We have solved it and we have found all the equations of x1t and x2t. We found that x1t is a constant term and we found x2t is a variable term, and how the x2t changes we have found it by MATLAB, and I have shown you. So this is the very basic of state variable system, the basics of calculations of state variable system, and how a state variable system can be solved to get the state equation and the graph. So this was more or less the basics of this thing, subspace based technique. Build on that, and there is controllability, observability thing remaining. So maybe while we are doing the actual course in system modeling, okay, there we might be saying what is the significance of controllability, observability, and how to use that, and how to know the system controllability and observability property and what are their significance. Okay, I stop here. That was all from today.